Oh putain! Oh putain! Oh putain de bordel. Ça a pris feu. Oh bordel de merde.
Yeah, so that happened. Excuse my French.
Putain de merde.
I am shit at actual electronics, even though I am smart. At least that is what my mom tells me. To make up for that, I decided to build my own electronic speed controller from scratch, because buying a $15 one from China was apparently too easy. Anyway, this is a story of how I spent 3 months learning new shit, almost died in a fire, and ended up with something that actually works.
Oh wow, okay.
Kinda. We'll get to that. So I want to build a drone from scratch, and drones have ESCs, or electronic speed controllers, to make the motor spin. And ESCs are super important because their role is to take the regular DC voltage from the battery and make the motor spin. Without this, there is no way to know at what speed the motor is spinning, and there is no way to make the motor spin at all because the motor won't take DC voltage. You can buy one for like $50 on AliExpress, it works great and everyone's happy. I did not do that. Instead, I decided to understand how they actually work because I absolutely need to make everything harder than it needs to be. And this turned into something way bigger than I expected.
Okay, what the fuck just happened?
And today we build the ESC, or at least we try to. Okay, so at first I had absolutely no idea about what I was doing. So I adopted a method that revealed to be extremely dumb. I went on the internet and typed open source ESC design and found a very simple open loop design. Open loop means it spins the motor blindly, but it was okay for a first run. The plan was to reproduce this exact circuit, throw in the code, then close the loop to make it a real ESC, and GG, easy project, or so I thought. So I ordered all of the components online, completely clueless about what they even did.
324, these are comparators, I think.
And then I built this horrendous circuit. I had no power supply at all, and still completely clueless, I hooked up a battery directly on the circuit.
Oh putain.
And of course it went wrong. I mean, I didn't even know what I expected to happen, but yeah. So back to the drawing board it is. So to control the motor, I decided to make a little perf board circuit for the prototype. But in the future, to make this right, I decided to go with PCBWay for the PCB manufacturing, which is sponsoring today's video. PCBWay offers a ton of PCB related services as well as CNC services and many more. I really recommend checking them out. The website experience is great, and without further ado, let's see how a BLDC motor actually works. A BLDC motor, or brushless DC, has 3 phases, as well as some magnets around it which can spin. And to make it spin, you need to energize them in the right sequence at the right time. And this is it. That's the whole goal, that's the whole purpose of the circuitry. To create this rotating magnetic field that will make the rotor spin. Which is super simple on paper, except it really isn't. These small motors, even though they seem small, can pull an insane amount of current. So you can't really power the motor via your typical Arduino. But if that's impossible, then how? How do we get current to flow from one phase to another then? Well, instead of using bare Arduino pins, we'll need to use beefy transistors called MOSFETs, which can handle high voltages and high currents. They can stick a phase either to VCC or ground. This way, we can make the current flow from one phase to another, which creates the electromagnetic field we need to make the motor spin.
Yeah, bitch! Magnets! Oh!
Except these MOSFETs are so beefy that an Arduino can't even drive them itself. In a nutshell, it means that we need a separate IC called the gate driver just to open the MOSFET.
These are whatever this is. Oh no.
The gate driver was also a pain, because you actually need to be good at electronics because of something called bootstrapping for those interested. Anyway, once that clicked, I had everything I needed and it was time to make the real motor spin. So I rebuilt the ESC circuit, this time using a breadboard to avoid wasting hours if it catches on fire.
Let me see what you have! No!
And because it was time to get a little bit serious, I got myself a little oscilloscope. It's pretty shit, but it does get the job done. I also got from my grandfather a 2-channel analog oscilloscope, and because before that I had absolutely no way to debug the hardware, which made any development impossible. And I also got a PSU, so that if a short arises, I don't risk dying in a fire accident. After building the circuit, I spent some time writing some shitty code and went directly for my first runs. It's actually looking pretty good. Look at that. If it works, it works. If it doesn't, oh f***. Okay, it's doing something. It doesn't look like it's drawing a lot of current, but these curves are definitely looking a little cursed. Okay, so this is far better. Okay, so with more current, it's definitely sustaining itself better. Okay, so it spins, but badly. Nothing ever goes right. I spent a good while convinced that it was a hardware issue. So I moved away from the breadboard and actually rebuilt the entire circuit on a perf board. And after all of that, it turns out it was indeed the code. Specifically, I was running everything in a loop like a complete dumbass, meaning the timing was pretty much random based on what the Arduino felt like doing this day. So I fixed it using interrupts-driven logic, which I was just too lazy to code until now.
Wow.
It got much better indeed. But we got another problem. The MOSFETs are getting pretty hot very quickly.
Yeah, the MOSFETs are heating up.
But where is all that power coming from?
They're getting hot, but it's like warm.
So I hooked up the whole analog oscilloscope, and that's when I saw it. Here, high side, this is channel 1, the low side. The MOSFETs can take a little bit of time to turn on and off, so if you are not careful, they may just short the entire phase from VCC to ground, which basically means I was creating a tiny short circuit on every single commutation step, more than 10,000 times per second. With that in mind, a couple of lines of code bring our 50 watts consumption down to just 5 watts for the exact same result.
4 watts, ce qui est beaucoup mieux que les 50 d'avant.
Les MOSFETs chauffent quasi pas. Which is absolutely great. For reference, we went from this...
Oh putain! Oh putain!
to this. And in the next chapter, we will try to actually close the back EMF loop so that the motor can actually generate some torque. By the way, if any of you know why my back EMF signals look so disgusting, I am really open to any tip. With that being said, smash that like button if you like the video, and I will see you in the next one.